I would like to introduce Dr. Humphrey Fonge from University of Saskatchewan, who will speak about mainly technetium radiopharmaceuticals. Humphrey received his master's in sciences and PhD in pharmaceutical sciences from KU Leuven in Belgium. Then he completed a postdoctoral fellowship at UFT in 2012 under the supervision of doctors Christine Allen and Ray Riley. And his postdoctoral work focused on the development of cancer theranostics using different biovector platforms. Dr. Fonge also holds a Master's of Business Administration from UFT. In 2013, he moved to University of Saskatchewan, where he's currently Associate Professor in the College of Medicine and a radiopharmacist with the Saskatchewan Health Authority. Dr. Fonge's research focuses on bench-to-bedside development of novel cancer theranostics, and he works under the four main pillars: the production and processing of pharmaceutical-grade diagnostic and therapeutic radioisotopes, development of targeted imaging agents with focus on image-guided surgical probes, near-fluorescent imaging agents, and development of alpha particle-labeled antibody and peptide therapeutics with the drug conjugates. And the fourth pillar, translation of novel imaging probes and therapeutics to clinical trials. Please welcome Dr. Humphrey Fonge.
Thanks for the very kind introduction. Good morning, everyone. My name is Humphrey Fonge, and I am an associate professor in the College of Medicine. I especially like to thank the organizers of the symposium for giving me the chance to talk about preparation and QC of technetium-99m radiopharmaceuticals for SPECT imaging. The learning objectives of this session are gonna read as follows. So first, I'd like you to understand basically the concept of radioactive decay. Particularly relevant to this talk is going to be technetium-99m generators. Then I'll review the some ideal properties of commonly used commonly used isotopes for SPECT imaging. Then I'm going to dive into basic coordination chemistry. So I hope you understand the basic coordination chemistry of technetium-99m based radiopharmaceuticals, and then an understanding of the fundamentals of QC of technetium-99m radiopharmaceutical compounding, fundamentals of QC-99m compounding and quality control. So again, in light with that, that pretty much reflects an overview of this presentation. I'm going to drive on some nuclide decay characteristics of technetium-99m. I'll talk a lot about technetium-99m generator. Production routes of technetium-99m, because this is going to be part of another talk for this particular session. So I'm just going to present this very briefly, just to set the ground on about where we get molybdenum that we use to constitute our technetium-99m generators. So that said, I'm just going to go ahead with the content of this talk. So basically, I guess most people here understand what radioactivity is, but just as a reminder, a radioisotope of an element is a particular variation of the nuclear composition of that element. The protons remain unchanged, electrons remain electrons remain unchanged, but the number of neutrons in the nucleus vary. So for stable nuclei, most light to middleweight elements, and especially those of atomic numbers up to 83, with the exception of technetium, are going to be stable. So technetium is the exception of those light to middleweight atoms. But most elements of atomic number above 83 are inherently unstable. So it is elements like radium-88 and uranium. So those elements are going to be inherently unstable. Then I wanted to make sure that we are on the same page with some of the symbols used for radioactivity. So basic equations, units, and so on. So the equation on the slide is just your basic fundamental decay equation, which actually says that the number of disintegration per time is proportional to a constant multiplied by the number of atoms remaining. And so using that equation, you are going to be able to actually calculate the number of atoms remaining at time t, which is going to be a function of the initial number of atoms you started with. Your decay constant lambda it's very peculiar for every atom, as that relates to the half-life of that nuclide, right? And then t is your time. So that's your fundamental decay equation. Of course, radioactivity units are in counts per second, millicurie, and 30 or becquerel or kilobecquerel, megabecquerel, and 37 megabecquerel is equal to 1 millicurie. And so this is basically an extension of that equation. And here basically I just had to define a half-life, which is 50% of that disintegration. A becquerel, which is equal to 1 disintegration per second, 1 dps per second, and 1 curie is 3.7 times 10 to the 10 dps per second. And so that said, I wanted to then go into what makes an isotope ideal for SPECT imaging. So I listed on the slide some characteristics. So that nuclide must emit a descent gamma rays. Descent meaning it has to be of certain within certain energy range, preferably no beta emitting particles, since these are going to be absorbed by the patient and contribute to the patient dose without necessarily being counted by the gamma camera. The gamma ray energy should be high enough to minimize patient attenuation. So ideally it should be above 100 kilo electron volt, and so that's the reason why things like thallium are not thallium 201 are not very good for imaging. And then the gamma ray should have low enough energy in such a way that it cannot be stopped by your sodium iodide detector in the camera. And therefore that puts an upper limit of about 300 kilo electron volt as well, and it should be capable of forming a complex with a variety of using a variety of radiopharmaceutical approaches and radiopharmaceutical chelating agents. And so another important characteristic is that the half-life should be reasonable enough to permit you to develop that to do that compounding and administration and then imaging. And so things like N13 are not very reasonable because of the very short half-lives. And also that half-life is important because it shouldn't be too long enough so that it minimizes radiation dose to the patient. And the radionuclide should be readily available and at a reasonable cost. So that said, I have a table here that shows you some of the important radioisotopes that have been used for SPECT. So technetium-99, and without a doubt, is going to be on top of that list. But also, there's things like indium-111, which we use for blood cell labeling. There's iodine-123 that you use for thyroid work. There's also the DAT scan that uses iodine-123, and then things like thallium that are ideally not very ideal for imaging, but have been used previously quite often in the past. So that said, you would now realize that technetium 99M is ideal. It's just the perfect isotope for SPECT imaging. IG gamma energy generators allow you to prepare your compounds on demand, but also to note that there's also often always Korea added amounts of technetium in that generator eluate. So on the slide also you will find the decay spectrum of technetium 99M, and again, like I said, like I just said, it's important to note that about 12% of your moly 99 decay bypasses technetium, bypasses to technetium 99M and directly to technetium 99. So something to note, because that has the potential to result to small issues around radio labeling. So technetium 99 is a staple in nuclear medicine. It's used in about 65% of all scans, over 45 million procedures a day worldwide. And so what do we use it for? So in a typical nuclear medicine department, the pie chart is a distribution of what your tech is used for. Perfusion, myocardial perfusion imaging it occupies the bulk of SPECT imaging procedures. But there's also bone scans for obvious reasons, because a lot of multiple cancers will have bone involvement. So MDP bone scan is a very popular technetium tracer. There's other things like infection imaging, some thyroid imaging, but tumor imaging not so much, especially in the era of precision medicine. Tumor imaging using technetium 99 and not so much. First, there's no approved tech 99M tracer for precision cancer diagnosis, but the reason can be obvious. Is mainly because I think, in my opinion, is the fact that we don't have that excellent specific activity needed to do some of such cancer imaging procedures. So that said, I said I was just going to go briefly on this the production methods for technetium, just so that we all know where the moly that is used to make our generators come from is coming from. And so, but because there's another talk in this session that really speaks to the different production routes for different isotopes. So four main methods. So the first one is just in your nuclear reactor using uranium 235. So U-235 is going to be bombarded with a thermal neutron, and that basically leads to the separation of both heavy products and light products, about 6% of which constitute moly 99. And your moly 99 then, again, like we said, is going to be used to build that generator that will eventually decay into technetium 99M, and some of it will bypass directly into technetium 99. And another reason why I just mentioned this is because all these different approaches may end up with different types of generator or different ways of you receiving that technetium in your nuclear pharmacy department. So this is particularly the case with the cyclotron production route. A lot of Canadian centers have really put in a lot of efforts to get cyclotron technetium approved by Health Canada. But what ends up happening is the fact that cyclotron technetium, cyclotron produced technetium is just going to be delivered to you to the radiopharmacy, I guess it's going to be in just lead sheeted vials of the final product, the final technetium itself, not necessarily as a generator. I guess those technologies are going to change over time, the way they are being delivered. But again, cyclotron production leads to direct production of technetium-99m, but there's also an indirect method using MOLY-100, using an electron linear accelerator. This is what we do locally in Saskatoon, headed by one of our local companies that uses the electron LINAC to do a photonuclide transmutation reaction on MOLY-100. And they end up having MOLY-99. And then if you've been to the US, the neutron capture method has been pioneered by quite a few American institutions, and this huge generator tank is FDA approved. And so this is the neutron capture method using your naturally abundant MOLY-98. So we don't have this generator system Health Canada approved as of yet. And so I just wanted to remind everyone why generators have been very important using the slide. So generators are readily available from a variety of suppliers. Radionuclides, they make radionuclides readily available for, they make the radionuclides in general readily available for compounding. Requires less specialized training from technicians. So not a lot of training needed to operate those generators and make those and compound those preps. The cost of the radionuclide is really very low. Usually no upfront cost to small nuclei pharmacy operations compared with things like cyclotron and electron linear accelerators. So there's no need for on-site bombarding facilities. The cost is low to really low to nuclear medicine operations. And so what happens is once you have that MOLY, you are going to use that MOLY-99 in this case. You are going to use that to build your generator. And these generators operate by two main principles, which I just want to review here. So you have that MOLY-99, which is a parent isotope, is going to decay over time. The half-life of MOLY-99 is 66 hours. And then as it decays, technetium-99m builds up in that generator. And so this is represented by this. So there's a daughter, there's a parent isotope that has a longer half-life, usually longer half-life compared with the daughter isotope, and as the parent decays, the daughter builds up. And so this equation is going to allow you to calculate the exact amount of that daughter isotope that you would have in your generator. And so this is the concept of the transient equilibrium. So there's a transient equilibrium, and of course, on the other hand, there's a secular equilibrium. So transient equilibrium is just when the half-life of the parent isotope is just a few times longer than the half-life of the daughter isotope, which is the case of MOLY-99, 66-hour decay, and the daughter isotope technetium-99, which is a 6-hour decay. And so this is how the buildup of technetium is governed. It's governed by this transient equilibrium. And so you can see this more clearly here in terms of the fact that your technetium builds up as your MOLY decays following that kind of decay arrow, and your technetium-99m builds up. The maximum tech activity, magnesium technetium-99m activity is about, it occurs between 22 to 23 hours. But you also have to remember that there's a maximum buildup of technetium-99 is after 10 hours. So after 10 hours, you start having a higher molar ratio of technetium-99. So again, making it critical to use just that fresh generator elute. And so then as you elute your generator, that build-up of the daughter, you actually extracted the build-up, the daughter that had been built up, and then you start again, it starts getting generated, it then grows again in the generator, and then you can elute, and that cycle keeps going until you are completely depleted of your moly, right? And then on the other side is what we call a circular generator, in which case the half-life of the parent isotope is far greater than the half-life of the daughter isotope. And so what happens is that it's hardly ever the case that the daughter builds up more than the activity of the daughter builds up more than the activity of the parent isotope. And again, this is the case with a generator system such as radium-226 that would and the daughter isotope is radon 221. And again, not to go into the details here, but this equation is going to allow you to calculate the amount of parent and daughter in daughter isotopes remaining. Now, so you have your moly 99, you're going to put it in the generator. Again, like I said, it's going to decay. But it's a very fundamental concept on how you get your pertechnetate, which is just the fact that moly 99 is going to be loaded into alumina support. Alumina is, of course, is positively charged, and just the differential charge between the molybdate, which is a -2, and your pertechnetate, which is -1, allows the molybdate to be more tightly bound to alumina, and then you can now use saline to elute your generator. So basically, that's what happens with your when you elute your generator. But the reason why this slide is important is because it allows you to understand why there's potentially breakthrough of what? Breakthrough of the moly itself, and even potentially breakthrough of some of the alumina, depending on the age of your column, or the age of your generator. And so this slide basically gives you a clue about what is the content of that technetium that you're going to be using. Just to remember that there's going to be never carrier-free technetium-99m, as you can see from this plot. So from this plot, you would realize that, again, like I just mentioned briefly a moment ago, there's going to be about 10 hours until you start getting more build-up of technetium-99 compared with technetium-99m as your moly decays. And this table is just going to let you understand how much is that build-up and what is the mole fraction of your technetium-99 compared with your technetium-99m. So very easy for you to come take a look at such a slide and understand when and how much is that build up. Because if your generator elute is too old, you're going to have a lot more technetium, and it's more difficult to reduce technetium to an oxidation state that allows for good labeling. So that's the reason why your stannous chloride, you will need a lot more stannous chloride to reduce technetium compared with how much stannous chloride you're going to need to reduce technetium-99m. Now, so once you have your technetium-99m, it needs to pass some specifications. So a couple of them, a couple of USP and European Pharmacopoeia standards. So very obvious things. So one of them being your elution efficiency, which is calculated by comparing the eluted activity with that of what is expected at that particular time. So that simple ratio allows you to determine your elution frequency, and that elution frequency needs to be between 90 to 100% of the theoretical moly 99 activity. So the next QC measure is radiochemical purity, sorry. And here I'm mostly thinking about moly breakthrough. You can determine that using gamma spec, but very easily you just would measure the amount of moly you have in your technetium eluate. So the amount of moly you will have per 1000 millicurie of technetium eluate is going to allow you to calculate what that moly 99 breakthrough is for your generator eluate. Radionuclidic impurity can be done using paper chromatography, using methanol water solvent. The retention factor for technetium 99M is 0.6, or as well using acetone and silica gel paper. And in that case, your moly has a retention factor of 1, while impurities such as colloid are going to have a retention factor of 0. Again, USP standard says that it must be greater than 99.9%. And then for chemical purity, you're looking at alumina that can potentially break through. That can be done using by colorimetry or atomic absorption spectroscopy. By colorimetry, just using standards, you will be able to determine how much of alumina you have in that sample. And then, of course, pH is supposed to be pH of saline. It's supposed to be 4 to 8 for injection, and then you would need to do sterility and pyrogenicity and endotoxin tests for that generator eluate. Then I'm going now into your coordination chemistry. And so the beauty about technetium 99M is the fact that you can form all those different complexes in different oxidation states. Now, the lower the oxidation state, the more stable that complex is. But a lot of these complexes, even +5, they are all very stable. And this is the beauty of the ability of technetium. Based on its electronic, based on the electronic configuration of technetium, right? So your pertechnetate is a +7 oxidation state. It will need to be reduced, and it's reduced, and that reduction simply happens by the loss of about 7 orbital electrons. And then once those 7 orbital electrons, up to 7 orbital electrons are lost, that allows incoming ligands with lone pairs of electrons to fill in those empty orbital shells and form that complex with technetium. Now, the oxidation state of that technetium depends on things like the pH, the reducing agent that you're using, and of course the overall charge of that complex also depends on the coordinating groups that you bring in. So pH reducing agent, because technetium can be reduced to +5 to +6 to +1 and so on and so forth. And so so this depends on those factors: pH reducing agent and the balance of all those things that would allow you to form a wide variety of complexes with technetium, right? So again, like I said, so depending on the extent which your technetium core has been reduced, you are going to have the situation where you can form stable complexes depending on different ligand types that are available to form that complex with those empty orbitals that have been left following the reduction of your technetium. So this slide basically tells you some different options of complex formation of technetium with different ligand groups. And so that said, on this table now, I have just presented the oxidation state of different technetium complexes that are used in a typical nuclear medicine department. So your per technetium, of course, like I said, is +7, and so is your complex with sulfur colloid. Maybe it's +1. Quite a lot of complexes formed with technetium in the +5 state, and that includes things like MAC3, HMPAO, ECD, gluceptate, and a bunch of others, right? So again, just a reminder that despite technetium being a lot more stable with at the lower oxidation state, these complexes have all demonstrated excellent stability for in vivo use. Now, so that was the case in which you would take technetium and you bring in all these different ligands to just form the complex. What if you wanted to label, say, a biomolecule such as a peptide and antibody? Now we have two main approaches. So there's a post-labeling approach, and then there's a pre-labeling approach. In the post-labeling approach, you will need a bifunctional chelating agent with an active functional group somewhere in the bifunctional chelating agent. It's bifunctional because on the one hand it can form this complex with technetium, and on the other end or some other side of that chelator, it should have these activated functional groups capable of forming a bond with a biomolecule. And so in that post-labeling approach, you are going to develop that molecule, constitute that molecule, hopefully with some reducing agent or some other agents that will allow you form a transition complex with technetium-99m, and then you are going to add the technetium, and then you are going to be able to have that biomolecule labeled with technetium. But there's also a post-labeling approach, which I always find tricky when I used to do this, which is the fact that you are first going to have to complex that technetium, and then depending on the functional group that you have on that bifunctional chelator, you are going to have to do things like dry it or reactivate the bifunctional chelator before you can add that biomolecule, and then you would have a labeling, a potential labeling approach. Now, the beauty about the post-labeling approach is that you may end up having a very high specific activity compound as opposed to the post-labeling approach. Now, again, like I said before, that bifunctional chelating agents have in practice we use quite a few different activating groups. So NHS esters are very common, but also there is isothiocyanide and melamine functional groups that are used to activate that molecule to allow you form that complex. Now, so that's said about the coordination chemistry of technetium. And so now we go to factors that would potentially affect your labeling. So I already mentioned the age of the generator, right? So it's recommended you use fresh L-weights less than 4 to 6 hours, less than 6 hours old. To reconstitute your product, because just simply because of the buildup of technetium. So maybe a 12-hour or older generator will significantly affect your radiochemical yield. And so again, and that is based on the fact that technetium-99m needs higher amount of reducing agents that may not be present in your kit to form that complex to eventually form the complex with your kit formulation. The other thing that always would affect any technetium complex you form is the potential for reoxidation. So you need to reduce technetium from a higher oxidation state to a lower oxidation state, but inadvertent introduction of air into that vial is going to reoxidize the technetium, and that is going to affect your labeling yield. The other issue you may have is autoradiolysis, usually at high concentration, so you always have to stick with the recommended radioactivity concentration for your kit, because at very high concentration you're going to have free radicals tending to reoxidize your technetium, and by so doing affecting your labeling yield. The ratio of technetium to stannous chloride in that kit has to be optimized. Usually for every kit it has been optimized, but just so you know that inadequate amounts of stannous chloride, of course, is going to affect your labeling, because you end up having a lot more free pertechnetate. And so some common fixes are listed on the slide. So use fresh generator L-weight. Do not add excessive activity to kits. Avoid high concentrations, highly concentrated solutions. Avoid introducing air, especially if you need to be pulling up samples from your labeling vial. Preferably use kits with some free radicals, scavengers or stabilizers stored in fridge. Of course, as recommended, do not use discolored L-weights, and if fractionating kits, make sure you don't introduce air into that kit. Now, when we make these preps, usually we would just a lot of the routine QC is ITLC, and so for ITLCs, basically you're going to use one or two different forms of paper chromatography and a solvent system and a small jar to elute that solvent system through your paper. And so there's different systems for different radiopharmaceuticals. All of this will be available to you in that kit package insert. So there's MEK, so acetone. There's also sodium chloride, and you basically are just going to spot and you wait for 1 minute, and it develops, and then you're gonna scan, or you're going to cut and determine the activity in a gamma counter. So that would allow you to calculate how much is it that you have in that prep. And so I just wanted to go through some basic preps, a few agents. So one of them being MDP. I mentioned here what MDP is used for. Things like metastatic disease, breast cancer, prostate cancer, all those different diseases or cancer types that will metastasize to the bone. There's osteomyelitis, an infection of the bone, and a few other bone conditions that show high metabolic uptake of MDP. So the dose for your MDP is 10 to 20 millicurie per patient. Imaging time is 1 to 4 hours. Approximately 50% is taken up in the bones in the skeletal system in 2 to 4 hours. Excreted, about 50% is excreted by 4 hours by glomerular filtration, and about 80% by 24 hours, right? So it's gone pretty quickly. But of course, a compromised renal function is gonna affect the excretion of your MDP, which will affect image quality as well. And so to prepare your MDP, it's very simple. You're gonna take out your pertechnetate and then boil. Your kit of typically consists of ascorbic acid as a free radical scavenger. Of course, your reducing agent and some excipient and stabilizer, and your API is methylene diphosphonate. And so the table now shows you your ITLC QC method for your MDP kit. Then I wanted to just go quickly and look at two other compounds. I'm talking about 99M ECD and 99M HMPAO. For ECD, your dose is between 10 to 30 millicurie, which is of course adjusted for weight and hepatic impairment. And then for HMPAO is 10 to 20 millicurie. So these are imaging agents that are used for brain perfusion abnormalities, be it injury or other brain abnormalities, such as acute or ischemic stroke, evaluation of suspected dementia. Again, like I said, evaluation of traumatic brain injury, inflammation, or even brain death, right? So something that is also very popular in a typical nuclear medicine department. So your kit is like your kit formulation for ECD is 2 vials. So there's the first vial, which is just which is mainly a buffer solution. You're going to add your tech to your buffer solution, and that kind of buffers that's kind of used to buffer that formulation. And then there is the second kit that has the API, and of course, which consists of stannous chloride and the ECD API and EDTA, and then you are going to add that buffered solution to your ECD kit, and then you will do a QC by paper chromatography, right? Paper chromatography, and that's basically how you prepare your ECD. And that's basically how you prepare your ECD. So for HMPAO, there's a stabilized stabilized formulation, and there's a non-stabilized formulation. The stabilized formulation basically consists of a solution of cobalt, which allows you to use this for up to 5 hours, without which the non-stabilized formulation is very prone to some to this disaggregation, and you cannot use that for up to 5 hours. Your HMPAO kit is the constitution of your HMPAO kit as listed. So there is HMPAO, the stannous chloride, and again in the table you have the QC method for your HMPAO. Okay, and so in summary, I have talked about some of the IG properties for SPECT isotopes, for which technetium, there's no other one better than technetium. We talked a little bit about the different routes to produce technetium, and what is currently available to us in Canada is the production of technetium using a U-235, what we call a fission moly. But there's also other methods, such as the cyclotron production cyclotron production method, and which is Health Canada approved, and in the US there's what we call the neutron capture method, which is also Health Canada approved. At the end of the day, what we currently use throughout Canada is our generator L-weight, using that fission moly. for which you would constitute that generator using Moly-99. I have reviewed some of the characteristics of that generator, and again talked about how you could use this generator to make different complexes using technetium-99m. We reviewed also a few of such complexes using technetium-99m. So technetium-99m is a staple in any nuclear medicine development for very obvious reasons that I stated. But we also see that there's there's a few new developments in technetium, such as compounds such as technetium-99 PSMA that are in clinical development that may even in some cases improve or increase the utility of technetium and technetium-99 based agents. With that, I'd like to thank you for your attention, and again to thank the organizers of the symposium. I am available to take your questions at the end of the session.
Thank you very much, Humphrey. How are you doing?
Yeah, good. Hi, Esther.
Okay, thank you very much. We have a little bit of time left for questions that we set up. So if there are any questions for our speakers, feel free to ask us. Esther, I was going to ask you, you had a list of approved products in Canada. I thought fluoride 18 was approved in a number of jurisdictions. Can you hear me, Esther?
Hi, Esther, can you hear me?
Oh, now we can hear you, yep. We can hear Mihaela. Can we hear Esther? Can we hear Humphrey?
Yeah, Esther, I can hear you. I can hear you, Doc. I can hear you, Mihaela, but Esther.
Okay, I can hear you as well. Esther, can you hear me? Oh, doesn't. Okay.
Doc, can you hear me?
I can hear you, Humphrey.
Sure, good.
Yep. So
okay, in the meantime, I have a question for Doug and Humphrey. Since many of the panelists today have been involved in the development of Tech-99m produced on cyclotrons, do you think, and I know you alluded a little bit during your talk, Doug, but do you think, is it still relevant given the new reactors that are coming online and the new method of production of Moly-99 on the reactor to have a cyclotron produced Moly?
Humphrey, do that.
Okay, so I think it's worth acknowledging the fact that the cyclotron produced tech that has held Canada approved is just the pertechnetate, right? So what hasn't happened yet is the fact that that pertechnetate is yet not licensed with any of the kit formulations, which is going to be a separate process. And I don't know how this either companies, because the cyclotron produced tech is now, I guess it's licensed to a separate entity called Artemis. So I don't know what that regulatory strategy looks like, because having the tech approved is one thing, but having that used with existing kits, which are only as of now approved for use with the generator system, I guess is going to be another long shot. So again, it depends on how much effort will need to be put to get those get that cyclotron produced approved with certain kit formulations. So that's going to be up to these companies. But in general, I think it's worth it. We have a whole bunch of cyclotrons in the country. I think that is something we should be able to do to maintain our own supply of tech. But again, there's all this, like you rightly said, there's all these reactors coming again online. I think it's like any business is going to be a matter of how that business shapes up, who is pricing at what price point, and so on and so forth. But again, like I said, the cyclotron produced tech is still gonna go some distance to getting that product approved with existing kit formulations.
Oh, thank you so much, Humphrey. I think that you've hit the word with one the thing with one word, business and economics. We have a comment from the floor here.
Actually, I would like to add, I happen to do also technetium with cyclotron in.
Hello.
Do you hear me now? Okay, excellent. So I happened to work on the project in Sherbrooke during some time before, and I would like to mention that Sherbrooke is still continuing and testing exactly what Humphrey mentioned right now, the kit preparation, and they showed that there is no difference with preparation of kits from cyclotron produced or generator produced. So it's really on the producers of generators now probably to make, not generators, but the kits to include it in their monographs that we can use technetate. So it's all business related, of course, and it's probably less relevant in Canada, but from discussions at IAEA meetings, it seems like there are developing countries or some countries which are having hard time to getting generators because it's either expensive or very difficult to get for different reasons. Then for them, cyclotron production of technetium might be something that they will look into using in future. So there is a potential, and the cost-wise, it's not so much more expensive than a generator one.
Thanks, Svetlana. And just to add to that, we have a couple of other authors in the audience that have also shown that it's cyclotron produced technetium labels all the kits, but again, it all comes back to economics and business. Esther, can you hear me?
Yes, I can hear you fine. Thank you.
Oh, good, good. I was just wondering. I thought a couple of jurisdictions did have fluoride 18 authorized by Health Canada some time ago, or has that all lapsed?
It could be that they have lapsed. So I checked out the database probably 3 or 4 days ago, and that was what I found. But it changes rapidly. Some leave it pending forever. So
yeah, no, yeah, that's what I was thinking. I looked it up, and you mentioned I shouldn't really say this, but I will. About the Health Canada website and clicking on there and going to find all this stuff, and I find their website to be kind of a bit of a rat's nest. It's kind of like you're doing Sudoku with your eyes closed.
yes, that's right. I think using Google is your friend. So I tend to not save links. I just Google, and Google finds it for me better than Health Canada can.
Yeah, actually, that's what you said. I actually missed that nuance there. Well done.
I also have a question for Esther. So I really enjoyed your presentation because you were capable to do something boring stuff, very, enjoyable to listen. And do you see any potential in Canada to avoid, or how we can solve this issue of disguising, established radiopharmaceuticals for imaging and not using them in clinical trials, so-called, which are not really clinical trials? Are there any pathway in Canada which we can envisage?
Not at the moment. I know that in the past workshops with Health Canada, they have spoken of a kind of an official pseudo clinical trial application, and they gave it a fancier name that escapes me at the moment. Doug, perhaps you remember, I don't know, but really, I think Health Canada will not really create a new pathway, because for them, creating a new pathway opens a huge regulatory kind of behind the scene, making it work with all the legal requirements. So it's a big thing. And unfortunately, the radiopharmaceutical sector is not really large enough in Canada to have sufficient clout to force a large behemoth and, you know, kind of bureaucrats that are not very agile in their way of operations to do something that works. So I'm a little bit pessimistic on that front, I have to admit.
Thank you.
Esther, I had another question for you. I didn't actually go into the SAP process like you and I had sort of discussed, and I ran out of time, so I didn't do anything about it. Do you have some experience with the SAP? I remember that was a method that we used many years ago, and Health Canada has sort of closed that door. Is it opening up again, or is it still closed?
So my experience with that is also some years ago from my time at the Montreal Neurological Institute, and it was a mess. So we filed for approval, for example, for 15 water scans for, I think, epileptic patients prior to surgery or something like that. I can't really remember. And then we got approval to inject them with radiopharmaceuticals, which we never asked for, which makes no sense. So they jumbled up the patient name, or the name didn't match the date of birth to identify. So it was a mess, and in the end, really, the physicians just didn't want to deal with it because it took a lot of their time, which they then couldn't spend on patient care, for something that in the end had very limited benefit. That being said, I remember from the last workshop that was held, that they said that they are looking into revamping and making it somewhat more functional. But I have not really seen any new initiative come out yet.
Yeah, I haven't either. Humphrey, you were nodding your head. Did you have something to add?
Yeah, I think that like Esther said, that program is a mess. I mean, recently there's been shortages of kits and you know, first of all, Health Canada doesn't want to be pushed around the place just because you need to have a product under SAP. So I think we've been having a few sessions with them to discuss about the SAP program. Hopefully they will revamp that program and really get a few things accessible for patients.
Mahela, did you have
we still use it. We still use it for DMSA access, especially for kids. And we have used it recently until Colette came back online for mebrofenin access again for kids. It is cumbersome. The rules change without us being notified, and it is tedious. But it's the only option we have now for certain radiopharmaceuticals.
Oh, thank you. Are there any other questions in the audience? Okay. I don't know what time it is. It's 15 after. We're actually ahead of schedule, but if there's no more questions from the audience, I think we can have a little early lunch. And then we'll reconvene. What time are we reconvening, Eric?
At 1:15.
Okay, 1:15.
Okay, I'll see you all then.
Thank you very much. Thanks, guys.
Thank you.
Thank you.
Thank you, Doug. Thank you, Michaela. Thank you, Esther.